This video is on transition metals and complex ions. There's quite a number of aims in this video, so first we need to understand what is meant by a transition metal and the properties they have, define the terms ligand, complex and coordination number, understand what is meant by unidentate, bidentate and multidentate with regards to ligands and know some examples of each one, know what a heme is, know the shapes of complex ions, know what shapes of complex ions can take and some examples of each and the reasons why different shapes are formed, and know why transition metal complexes are coloured and what affects their colour. So here's a picture of the periodic table, and we know that the transition metals lie in the D block. So this is the D block, but actually transition metals are not all of these. The transition metals are the following. So from group 4 to group, well, I say group 4, from titanium to copper in that period. The reason why scandium and zinc are not transition metals in that period is due to the definition of a transition metal. And the definition of a transition metal is that the element forms at least one stable ion with a partially filled d orbital. So scandium only forms scandium 3+, which means there are no d electrons in scandium 3+, and zinc only forms zinc 2+, which means it has a complete d block. So neither of those are partially filled. So a transition metal is a metal with where it forms at least one stable ion that has a part full or partially full d shell of electrons. These have certain properties, and those properties are variable oxidation states, they have colour, so they form coloured compounds. Obviously the metal themselves aren't coloured, they're usually grey. They can be catalysts, so they have catalytic properties due to their variable oxidation states, and they can form complexes, which is what we're going to be talking about in this video. So to define these three terms, I'm going to use an example, and that example is going to be a compound that you've used a lot in school, and that is aqueous copper sulfate. Now, when copper sulfate is dissolved in water, it actually forms something called a complex, and that is where the copper ion and the sulfate ion separate, and then the water molecules that are surrounding the two ions actually form dative bonds with the copper, and that forms something called a copper Hexa or Aqua ion, which is an example of a complex ion. So this is mainly made up of copper with 6 waters around it in an octahedral formation. And it's the oxygen that forms the dative bonds, so we'll draw the bonds from the oxygen. And the fact they're dative bonds means we can draw arrows at the end of these. And the fact that water is neutral and the copper is copper 2+, that means that this will have an overall charge of 2+. So that is an example of a complex ion. A complex ion is defined by being a central metal atom, or central metal ion, surrounded by datively bonded ligands. Now I've just used the word ligand there, so we need to explain what that is. So the ligands here are the water molecules. So a ligand is basically a molecule or an ion that will donate a pair of electrons to the central metal ion, forming a dative bond with it. So this is an example of a ligand, this water. So a molecule or ion that will donate a pair of electrons to form a dative bond or coordinate bond with a central metal ion. Our final word we have to define here is coordination number, and coordination number is basically the number of times a dative bond is formed with the central metal ion. So in this case we've got a coordination number of 6 because there are 6 dative bonds being formed with the copper 2+ in the middle. So a coordination number is just the number of dative bonds that are formed with the central metal ion. This is not necessarily the same as the number of ligands, because some ligands can form 2 dative bonds, or 3, or 4, or 5, or 6 to the central metal ion, which is what we're going to look at now in the next slide. So, these are 3 examples of ligands that you need to know about that can form more than one dative bond with the central metal ion. So first just going to understand what is meant by the terms unidentate, bidentate and multidentate. Basically, unidentate describes a ligand that can form one dative bond with a central metal ion. So unidentate will be things like water or ammonia or Cl- or Cn-. All of these can donate one lone pair to the central metal ion and therefore form one dative bond with it. So these are all unidentate. These two, there and there, these are both bidentate. They can both form 2 dative bonds with a central metal ion. This top one is called ethane 1,2-diamine, and this bottom one is called an ethane dioate ion. And you'll see that the top one's got 2 ammonia, or 2 nitrogens, if you like. Both are a lone pair, so it's the 2 nitrogens that form dative bonds with the central metal ion in that case. And in the bottom case, the ethane dioate ion, it's the 2 negatively charged oxygen that form dative bonds. They both have a lone pair as well. So both of these are known as bidentate ligands. Because they can form 2 dative bonds. And the ethane dioate ion can be written C2O4 2-. The one on the right here is called EDTA. You don't have to really worry about what that stands for. So you don't have to use, when you're using this in an equation, you don't have to use the whole molecular formula. That would be far too long. Instead, you can use EDTA as your instead of writing the molecular formula. And there are 6 different lone pairs here that will form dative bonds. Now actually, when EDTA forms a complex, these H's on the carboxylic acid groups are lost and they form negative charges. So actually EDTA is EDTA 4-, and you've got to take that into account when you work out the new charge on the complex ion. And the 6 bits that can form dative bonds are the 4 OHs, or are the 4 O-, sorry, they were OHs. So they each have a lone pair they can donate, and then the 2 N's in the middle also donate a lone pair. So this is known as a multidentate ligand. And multidentate is defined as a ligand that can form more than 2 dative bonds to a metal ion. This one in this case can form 6. So a heme is a multidentate ligand that occurs in biological systems. The most common one being, or the most commonly known one being, the one in hemoglobin. And a heme complex, you don't need to worry about the detailed structure of the heme complex. You need to know that it makes 4 dative bonds. and in hemoglobin it's to an ion. So what you get is iron with 4 dated bonds around it, and this heme complex is all connected, and it's the nitrogens in the heme complex that form the dated bonds to the iron in the middle. In hemoglobin, you then have a protein dated bonded to the top, which is known as the Globin protein, and underneath usually there is water, but this will be replaced by oxygen when there's oxygen present. Now oxygen binds fairly weakly with the iron centre, so when the hemoglobin gets to where it's needed in the body, then the oxygen leaves and the hemoglobin goes back in the blood to the lungs to grab some more. However, if carbon monoxide is present, CO, then that will bond strongly with the iron complex and form a stable complex, and therefore the carbon monoxide won't come off at all when it's in your body. And that basically renders the hemoglobin useless and poisons you, and therefore kills you in the end due to a lack of oxygen getting to the cells in your body. So we need to also know the shapes that complex ions can take, and well, at least one example of each one of the reasons why the different shapes are formed. So the most common shape is the octahedral complex, which is when there's a coordination number of 6. So if we've got a coordination number of 6, then an octahedral complex is usually formed, and any Hexa or Aqua complex is suitable as an example of this. So we're going to use the copper Hexa or Aqua complex that has 6 OHs or H2s around it, or H2Os rather, waters. And that is going to be a 2+ charge overall, and your bond angles here are 90 degrees between each of the ligands. So that's a coordination number of 6. And then you can also have a coordination number of 4, for which there are 2 shapes you can have. So the first one being a tetrahedral. An example of a tetrahedral complex would be copper chloride. So Cu with 4 chloride ions around it. So the reason why swapping the waters for chlorides will change the shape and the coordination number is basically, well, very simply put, is the chlorides being much bigger in terms of shells of electrons than the water molecules, and therefore you can't fit as many round the copper because they will start repelling each other. You've got 4 chloride ions each, a negative charge. Copper in the middle is 2+, and therefore overall this has a charge of 2-, and the bond angles here are 109.5 degrees for a tetrahedral complex. The other shape with a coordination number of 4 is square planar. And an example of a square planar complex would be a complex called Cisplatin, which is an anti-cancer drug, and it has platinum in the middle, and on the outside we've got square planar complex. On the outside we've got 2 chlorines, and we have 2 ammonias. Now cis is another way of saying Z in terms of EZ isomerism. So cis basically means that the 2 things are on the same side. So your chloride ions will both be on the same side on this side, and your ammonias will be on the same side on this side. So that is cisplatin, an example of a square planar complex. The final coordination number you need to know a shape for is the coordination number 2. And this will be a linear complex. And an example of this is Tollens reagents. So you've got silver in the middle, and then you have ammonia on each side. And then this will have an overall charge of 1 plus. So, there's a number of different reasons why transition metal complexes have different colours, and these pictures and video will show you, well, try and demonstrate different reasons. So this first one up here, set of pictures, shows different complexes of copper. So here you've got copper carbonate, here you've got copper sulfate, which is basically the Hexa Aqua ion. Here you've got copper with 4 ammonias attached to it and 2 waters, and this is copper oxide. So we've got copper carbonate, which is green. We've got the copper Hexa Aqua ion, which is blue. We've got copper with 4 ammonias and 2 waters, I'm not going to write the rest, which is deep blue, and we've got copper oxide, CuO, which is black. Here, none of these compounds have a different oxidation state of copper. Copper is always 2 plus. So the thing that's changed here is the ligand. So a change in ligand can change the colour. Down here, this picture, we have 2 different complexes. One of them is blue, one of them is pink. This blue one is cobalt chloride, and this pink one is the cobalt Hexa Aqua complex. Now in this case you could argue that I'm also showing you a change in ligand, but actually I'm also showing you a change in coordination number. So the other thing that can affect the colour is a change in coordination number. So here we've gone from 4 to 6 or 6 to 4, depending on which way around you're thinking about it. Coordination number. And then this video shows you the other thing that can affect the colour, which is a change in oxidation state. So here you're going to see vanadium being reduced by zinc and going through some different oxidation states. So just watch this. So you can see in that video the vanadium, the initial vanadium VO2 plus yellow being shook up with some zinc, and it got reduced down to VO2 plus, which the vanadium has a +4 oxidation state, down to V3 plus, which has a 3 plus oxidation state, down to V2 plus, which has a 2 plus oxidation state. So each oxidation state had a different colour: yellow, blue, green, and purple. So that's the other thing that can affect the colour. The reason why complexes have colour is due to the fact they have partially filled d orbitals. So if you were asked a question on why they have colour, you'd say that so the reason why they have colour is due to the fact that when transition metals form complexes, the d orbitals, which in the metal all have the same energy, suddenly split in energy. And in an octahedral complex they split so that 2 have a higher energy than the other 3, and in a tetrahedral complex they split so 3 have a higher energy than the other 2. So if we take, for example, copper, which has 9, or Cu2 plus, which has 9 d orbitals. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 in the octahedral complex, and 1, 2, 4, 6, 7, 8, 9 in a tetrahedral complex. You can see that there's a space in one of the d orbitals, which one of the electrons in the lower set of d orbitals could be excited into. Now, the complex would have to absorb energy in order for the electron to be excited. And it just so happens that the distance, the energy gap between the upper and lower d orbitals equals that of visible light. So visible light will be absorbed so that the electron can be excited up to the vacant d orbital, and the light that is not absorbed is the colour that you see. So if you had to answer a question on this, you would say that light is absorbed, or a colour of light is absorbed, electron is promoted or excited to a higher d orbital, or a higher energy d orbital. Therefore we see colour that is not absorbed. Let's look at a few examples of questions then. So in this one it says 3 characteristic properties of transition metals are complex formation, coloured ions, and catalytic activity. State the feature of transition metal ions that give rise to these characteristic properties. So that is the fact that they have partially filled d orbitals. And then it says, state a 4th characteristic property of transition metals, and that's the fact they have variable oxidation states. And then it says, for each of the following shapes of complex, identify an appropriate example by drawing its structure. So a linear complex. So the linear complex example was the Tollens reagent example, which is silver in the middle, with 2 ammonias on either side. And then ammonia is neutral in terms of charge, silver is 1+, and therefore this has a 1+ charge overall. A square planar complex, so the example that I showed you was cisplatin, so that's platinum in the middle, and 2 chloride ions on one side, and 2 ammonias on the other side. This has no charge because platinum has a 2+ charge, but it also has 2 chloride ions attached to this, which cancels out that 2+ charge. And then a tetrahedral complex, an example could be cobalt or copper chloride. So we'll use copper chloride, which has 4 Cl's around it, 4 chloride ions. Copper in the middle has a 2+ charge. The chloride ions each have a -1 charge, and therefore overall this has a 2- charge. So this next question says, transition metals and their complexes have characteristic properties. Give the electron configuration of a Zn2+ ion. Use your answer to explain why the Zn2+ ion is not classified as a transition metal. So the electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, because remember the 4s electrons are removed first. And the explanation is that it has a full d shell, or it does not have partially filled d orbitals. So the definition of a complex is a transition metal ion that is datively bonded to one or more ligands. Then it says, identify one species from the following list that does not act as a ligand. Explain your answer. So if we're looking for something that does act as a ligand, we're looking for something with lone pairs. So CO has a lone pair on the oxygen. Oxygen has lone pairs on the oxygen as well. O2 minus has lone pairs on the oxygen. It's hydrogen that has no lone pairs. If you draw hydrogen out, H2, you will see that all the electrons are in the bond. It has no other electrons other than those two in the bond. So not a ligand is H2. And the explanation is it does not have any lone pairs. And then identify one species in the following list that does not act as a ligand again. Oh, that's the one I just answered. Sorry, I didn't realise I'd copied it twice. So we'll move back down. The element palladium is in the D block of the periodic table. Consider the following palladium compound which contains a sulfate ion. Give the oxidating state of palladium in this compound. So a sulfate ion, if you think about H2SO4, must have a charge of -2. So that's 2 minus. Ammonia is neutral, and therefore the palladium must have a 2+ charge. And it says, give the names of 2 possible shapes for the complex palladium ion in this compound. So it's got 4 ammonias around it, so there's 2 possible shapes for a coordination number of 4. That's tetrahedral, and square planar. And the next question, in a complex that has been formed, 2 water molecules opposite each other, it says draw a diagram to show how the ethane diarrhea ions are bonded to a copper ion and give a value for one of the OCUO bond angles. It says you are not required to draw the water molecules as well. So remember that the ethane diarrhea ion is the following ion, C, double bond on both sides to an O, and then O minus, O minus. So it's this the 2 O minuses that form dated bonds to the copper. So what you'll have is copper, and when you're drawing these, I recommend that you draw the dated bonds first, just so you get everything in the right position, and then your oxygens that are doing the dated bonding, and then to your Cs, and then draw your double bonds from those Cs. So that'll get you a couple of marks, and then the bond angles between this, that's between the O, CUO, that's going to be 90 degrees. So bond angle is 90 degrees. And then finally, it says state the electron configuration of a Ti3 ion and that of a Ti4 ion. Explain in terms of electron configurations and electron transitions why Ti3+ compounds are usually coloured, but Ti4+ compounds are colourless. So Ti3+ is going to be 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d1. And then the titanium 4 is going to be without that 3d electron. So 1s2, 2s2, 2p6, 3s2, 3p6. So, it says in terms of electron configuration and electron transitions, why Ti3 compounds are usually coloured, but Ti4 compounds are colourless. And the reason is basically because the Ti3+ has a d electron that can be excited. So Ti3 has a d electron that can be excited or promoted to a higher d orbital, and will absorb visible light. Ti4, however, does not have any d orbitals, or d electrons, sorry, that can be promoted, and so does not absorb any visible light, and therefore does not have a colour.